or less on time.
Okay, in 2 minutes.
In 2 minutes? Okay.
You can see the NIST clock up there.
Oh, wonderful. Yeah.
This defines what time is, isn't it, in the universe?
Oh, it's all right.
At least in the USA.
Yes.
So long
That's
as the network's
right,
working,
that's
and that
right.
clock can talk to you, the server.
NIST is responsible for doing time in the United States.
That's right.
And
That's
the person who's in charge is Judah Levine, who's one of our fellows who lives here.
wonderful. Wow. That's,
So you,
I'm honored to actually be able to use that clock for my talk.
time that goes on there
It's all
him.
exactly. Oh, so.
Okay, and who's in charge? Are you in charge of doing the
Andrew will hit it,
Okay.
probably.
I'm lost.
Let me just quick.
Started in 1 second. Okay, hello everyone, and welcome to a normal colloquium, I think. We have Daisuke Nagai with us from Yale University. He's a full professor there, and I've had the pleasure to work with him a lot last year and a half. I think you started out, actually, your research career here, sort of at CU, right? As an undergraduate, visiting student with Dave Nesbitt. And then after that, you went to Michigan and then PhD at Chicago, Caltech, and then he's been at Yale for, 15 years now? And he's this mythological figure in the cluster simulation community. I didn't really know you until, he's the type of person who will give a whole week of talks at every talk event at CFA, like he did in 2018. So we're lucky to have him here. So Daisuke, take it away.
Great. Thank you very much. Can you hear me okay? The sound is okay? Well, thank you, Ben, for a kind introduction. It's such a pleasure to be here at the University of Colorado Boulder. Where I actually started my research endeavor. I was at the I was actually here for a semester in the winter of 2017. My wife is actually a graduate of University of Colorado in psychology department right across the street. So I was here for a semester taking physics classes. I think it was a statistical mechanics class and a few other astronomy classes during that time. And I also did a summer internship, my first summer research with the Dr. David Nesbitt here, actually doing a first computational simulation of deuterium fluoride trimer So it was an interesting molecular dynamics simulation, which at the end I was very proud to create a movie of the DF trimer, which was the system that I was simulating, and I first learned it was back in Fortran. I was coding in Fortran and did my first computational project there, and since then the rest is the history that I ended up actually liking it so much that I'm doing the simulation today, presenting the simulations of the universe and how simulation can be used to learn about cosmology and astrophysics. So just want to start with this figure to kind of put us in perspective over the past several decades. We've learned a great deal about the initial condition of the universe from the CMB experiments, which has taught us that the universe seems to start with the tiny ripples of fluctuations, which was inflated by the inflation. What we're seeing is that we believe is the ripples of quantum fluctuation inflated by the inflation of the universe that sets the seed for structure formation. In cosmology, we have extremely well-defined initial conditions that we can use as a starting point for any simulations of the universe to study the rest of the formation history of the universe. On the right-hand side, which we then see the distributions of galaxy from Sloan Digital Sky Survey, for example, and that from just by looking at these pictures, it's clear that universe started out from very inhomogeneous tiny ripples of fluctuation to highly inhomogeneous universe filled with clusters of galaxy, large-scale filaments, and galaxies, which has a much richer, very nonlinear structure. And one of the important points here is that delta rho over rho, the fluctuation in density field of the universe smoothed over the megaparsec scale, used to be very tiny fluctuation, now has been inflated to much significantly greater than 1, so that the evolution, nonlinear evolution of those density fluctuation in the universe is the key. This is the realm that requires numerical simulations to fully understand how the universe transitioned from this state to this state. Along the way, we've learned that the universe is filled with dark energy and dark matter, which makes up more than 95% of the stuff that we know about, that we don't know what they're made of. The stuff that we knew about in particle physics, like atoms and molecules, makes up about 4% of the energy density of the universe, which is what we mostly probe in the form of, and most of them are in gaseous form that are accessible in X-ray emission. Also, you can use CMB to study those warm gas, as well as the absorption lines from UV spectrum in order to study those gaseous medium. And of course, that even smaller percentage of that are in the form of stars, which we can also trace using galaxy surveys. And much of the cosmology experiment that are being designed are ranging from microwave to optical, as well as all the way up to X-rays and gamma rays, are designed to gain information about how the structure forms and grew, including galaxy, black holes, and clusters of galaxy, and of course those large-scale structures. So that's the goal, the landscape of where we are in cosmology and astrophysics. We're in the era of multi-wavelength astronomical surveys, and these are just a very small list of plethora of multi-wavelength survey. eROSITA, Russian-German mission, which has been flying and taking data until the war has started, but it actually produced a very beautiful image from and that gives us actually new views of the X-ray universe with the sensitivity that's 30 times better than the previous generation of X-ray survey called ROSAT. On the microwave side, we have a Simon Observatory coming up, as well as CMB-S4 being designed for the next generation to push the sensitivity and resolution of the microwave experiments to the next stage, and that these X-ray SZ experiments are complemented by the galaxy survey like DESI, Rubin, Euclid, and there are many that are underway, and that together they will provide the multi-wavelength views of how the universe forms and grows all the way from the CMB up until the present day. So this just gives you a brief status of where we are in using, for example, the CMB experiment, such as the South Pole Telescope that Niels has been playing a significant roles here at Colorado, also combined with Atacama Cosmology Telescope in Chile, and also Space Mission Planck. They together create have detected about over 1,000 massive galaxy cluster using CMB technique. The technique is based on the idea that you can use CMB as a backlight. These low energy photon, when it traverses through the hot electron that are embedded within massive galaxy clusters, for example, which is the excellent reservoir of hot electrons, that CMB photon experience inverse Compton scattering, meaning that the hot electrons are imparting energy back into the photon, scattering the photon up in energy, so that below certain frequency, critical frequency, 217 gigahertz, you see hole in the CMB sky in the direction of galaxy clusters. Above 217 gigahertz, you see additional increment in CMB photon because that low energy photon has been upscattered. And then that it creates this very unique spectral signature that allows us to unmistakably detect galaxy cluster actually out to arbitrarily large redshift. Because, and the redshift independence comes from the fact that this is a scattering process. This effect, inverse Compton scattering, often known as the Sunyaev-Zeldovich effect, named after two Russian scientists who proposed this technique as a way for cosmology, basically is that as long as the massive galaxy cluster exists and electrons exist somewhere between CMB and us, that scattering process do occur, and that would actually make it excellent way of probing galaxy cluster at the arbitrary large redshift because it doesn't matter where the galaxy clusters are. This is in contrast to, for example, X-ray emission technique. If you have an emissive probe, like a light bulb, say X-ray emitting galaxy clusters, for example, for X-ray telescope, if you put that X-ray emitting source out to larger distances, of course, the amount of flux that you receive goes down by 1 over distance square, and there's also cosmological dependence, so it goes down even faster than that. The more distant objects are generally significantly harder to detect in any given telescope. SZ effect, for example, in CMB does not suffer from that cosmological dimming. This is why we have this very uniform mass limit. This is the mass of the object that's detected using these 3 experiments so far, and that it has detected most of the object about 2 times 10 to the 14 solar masses. These are massive galaxies or intermediate-sized galaxies, and there's a very clean threshold here. It's almost mass-independent probe of these massive objects. So that's really promising, but the future of this is even more exciting because you can make the detector even more sensitive, making things higher resolution, getting better control on foreground, so that these are the expected sensitivity for the planned CMB S4 wide survey, ultra deep survey. If you go ultra deep, you can make your sensitivity even lower, probing the mass scales down by another order of magnitude lower than where we are, and that would promises to actually detect, instead of currently 1,000 objects, we expect to increase the sample size by about 3 orders of magnitude. 100,000 objects in the universe will likely be detected, because if you go to a little bit lower in mass, you have exponentially larger number of galaxy clusters, so that just by going a little bit lower in mass can give you orders of magnitude enhancement in terms of statistics. So in terms of statistics, that we're not really in the area of cluster cosmology, the idea to use galaxy clusters to learn about dark energy and dark matter, or even neutrino mass, we're not really limited by the statistical power of the current instruments, but the name of the game over the next 10 years or so is going to be understanding what we are observing and having a systematic uncertainty controlled at the level comparable to the statistical power of the survey, which are going to deliver in the next few years. This is just a constraint plot that people typically talk about when you're writing the proposal to grant agency. This is a constraint on omega matter. The amount of dark matter in the universe is of order 28%. Sigma 8, the root mean square fluctuation averaged over about megaparsec scale. It just sets the amount of fluctuation we expect on cosmological fluctuation on the 10 megaparsec scale. So that's important, because if you have a higher sigma 8, means that you expect to form significantly more galaxy clusters. If you lower sigma 8, your number of galaxy clusters are exponentially sensitive to the sigma 8. Another thing that people talk about is the W0 and WA equation of state of dark matter, pressure divided by the density of the dark energy, and how the time changes, how the dark energy changes the function of time, and these are the constraints expected from the eROSITA survey, which will also expected to detect 150,000 objects down to galaxy groups. This is a similar forecast for the CMB S4 survey combined with the optical, and that the kinds of the constraint that you can get on even, for example, neutrino mass. Neutrino mass you can imagine if it has enough mass, then it can serve as a warm dark matter candidate, smooth out some of the fluctuation in the large-scale universe, so that by studying the counting number of objects, you are also sensitive to how much smoothing that might have taken place due to streaming motions of the neutrino that would reduce. If more mass in neutrino means that you reduce number of clusters because you smooth out the density fluctuation, which is suppressing the formation of massive clusters. So you get some constraint that's actually of order milli-electron volts, which is getting into the very interesting range, which will allow us to check things like the inverted hierarchy problems in neutrino physics. So the case for cosmology is very strong. Experiments are underway. We're going to get the data. The question is whether we can actually deliver this. The big challenge that we're facing is to actually how to synthesize these large, big data sets from telescope, for example, of order petabytes of data, to then developing a theoretical model that's just as accurate to interpret the statistical power of all of these surveys. So this shows you how the telescope data, you will create maps like the one that I showed before, but then from these maps, you actually, the astronomers, cosmologists, they invent some summary statistics that allows us to summarize for example, the correlation function of the galaxy distribution as a function of separation, which contains a lot of information about the clustering statistics of galaxy, for example. We can do similar analysis in CMB survey, and then you crank through but you need also the model that is equally accurate to take advantage of all of these small error bars, and then you try to extract cosmological parameter through some kind of statistical framework in the middle. But in order for us to interpret these beautiful measurements of big data through this chain, we also need equally accurate and also the large simulations that are specifically designed for these survey. So the working horse in computational cosmology is to first run the n-body simulation that models the evolution, nonlinear evolution of dark matter component of the universe. And then also more recently, modern hydrodynamical simulation, which also follows gas, have a prescription for forming galaxies, and how galaxies interact with the surrounding gas. Very much the very active area of computational and cosmology and astrophysics. But once you have those simulations, you can also turn the crank. It also creates equally large data set as the actual observational data set. We go through the same analysis pipeline. The main challenge here is to try to develop things like emulator. You want to emulate the universe as accurate as possible for different types of cosmology, different types of astrophysics, and that's the main challenge that we're facing. If you can do this and complete this pipeline, we are bound to be able to actually get the excellent, exquisite constraints on the composition and nature of dark matter, dark energy, and also the nature of gravity on large scale. So we know exactly what needs to be done. We also have challenges. Let me just summarize that the main opportunities are for us to maximize the scientific potentials and return of these multi-wavelength survey that I was just talking to you about, and there's so many more that I cannot do justice introducing all of those exciting experiments and where the data are coming from. Main challenges are how the dark matter, how the gas and galaxies, things that we can observe in multi-wavelength observation, how they follow the dark matter halo, so-called halo galaxy gas connections, is one of the biggest challenges that we face if we were to do this. That the problem is inherently very complicated and challenging because it's a multi-scale, multi-physics nature of the problem, which I will get into in a little bit more detail. Another aspect of challenge is the big data challenge, that both observational and simulation data are actually getting larger. The large enough to the point that it requires special hardware like high-performance computing. It also provides opportunity for something like a machine learning that are designed, that just happens to be available for us to possibly use this because they are particularly good at identifying patterns and the features in large data sets. So maybe that might actually help us improve some of our modeling in the future. We don't know exactly how, but there are people who are starting to explore the potential new directions in that directions. So I will talk about that this is a multifaceted interdisciplinary program in astronomy, but also involving the data science and computational science. I'll briefly give you, I'm going to make 3 points. There are four frontiers that I'd like to tell you about. Computational frontier, modeling frontier, more focused on physics, machine learning frontier, and more focused on data-driven approach to this problem. I really like to have both because the data-driven approach might sometimes miss fundamental physics and physical intuition. Sometimes having a simple model continues to be very useful path forward. So I think that really embracing both approaches and taking pros and discussing pros and cons of those approaches, I think is the healthy path forward on this endeavor. And I'll just say a few words about low noise, high energy, high resolution frontier, which are enabled by continual improvements in the detector technologies. So I'm just going to quickly go through I'm going to make 4 cases for each of these frontier. One is the computational frontier. The key insights, the reason why this is a new frontier is because of the emergence and maturity of hydrodynamical cosmological simulation. I will just show you one example of what we have done. There are many projects like this. So I'm not summarizing the state of the project, but rather introducing our project just as a guide to give you an impression of the kinds of computational research that we do. This is Omega 500 simulation project, 500 megaparsec box simulation performed with the adaptive refinement tree code, hydrodynamical cosmological simulation code. Basically follows the evolution of dark matter. We have a 2-second fluid following the gas, so that we're solving Navier-Stokes equation for hydrodynamics, which is instead of collisionless equation, where collisions are set to be 0. Here we have collisionality because of the Coulomb collision that gives rise to things like viscosity. And then that we also have in high density region, we have a subgrid physics of galaxy formation, black hole formation, which are kind of put in by hand based on some phenomenological prescription. So that's probably the most uncertain aspect of this problem. In this particular simulation that I'm going to be telling you about is a 500 megaparsec box with the 65 galaxy clusters zooming in on those regions using adaptive mesh refinement technique, focusing on 3 times 10 to the 14, roughly matches the mass threshold of the CMB surveys, which we're basically designing this project to do, and that we wanted to make sure that we understand the non-radiative gas physics, hydrodynamics, as well as the effect of galaxy formation, effect of aging feedback. So we run these experiments with these knobs turned on one at a time. And instead of going through the specific results, I'm just going to summarize that there are 2 things we learned from doing these kind of simulations. One is that I'm going to separate this in terms of scale. First of all, in galaxy clusters, the most massive object, and if you're trying to make accurate models of it, I would argue that the cluster cores, inner about 20% of the virial radius of the galaxy cluster, continues to be very uncertain. We're not ready to use these regions to do cosmology whatsoever, in my opinion. Reason is that we actually have the physics that's stopping us from doing this or controlling, being able to model this accurately enough are the physics of heating, cooling, and plasma physics. They are all very important. We don't have these under control. Especially AGN feedback through mechanical versus cosmic ray heating is the outstanding issue. A lot of researchers are working on it. Very active research area. We don't have that control in terms of the cosmology readiness. Dynamical heating and gas slushing. The galaxies are falling in and conversion of orbital energies of galaxies into heating of the gas. That's much better understood. Still, we don't have enough resolution to fully capture its effect, but that's as less of a concern. And that the thermal conduction, magnetic field, and even things like some plasma physics, which I will talk to you about a little bit is actually stopping us from making the cluster core modeling to be sufficient accurate. Most important being AGN feedback remains sufficiently phenomenological at this point that we don't have a very good control on this physics. On the other hand, if you go outside of 20% of virial radius and into the outskirts of galaxy clusters, we've learned, well, this is an area where the X-ray telescope hasn't provided very much information. This is a new area, so that's a new frontier. SZ observation, because it's more sensitive to the outer region, it's linearly proportional to density as opposed to a square of the density like X-ray emissions are sensitive to. We've got a lot of information. We've learned a lot of physics, but the physics of outskirts of galaxy clusters are fundamentally different from the physics of galaxy cluster core. Especially AGN feedback, its effect seems to be somewhat contained within this inner region, doesn't seem to significantly perturb the outskirts of galaxy cluster. The potential is just simply so big that the burst of AGN just doesn't propagate that far in radius. On the other hand, we actually learned a huge list of things that actually affects the outskirts too. So this is the one thing that's more of a prediction from simulations. We first learned that there's the significant turbulent motion. Galaxy cluster form through mergers and accretion and continual accretion, especially late formation, so that the galaxy clusters are big because they're accreting material in recent time, and therefore they are also very turbulent. There's a significant bulk and turbulent motion, both mixtures of that gives rise to significant amount of non-thermal pressure, which increases toward the outer regions of the galaxy clusters. If you don't have a good models of turbulence, we are going to be missing the information to use CMB as a way of cosmology used through SZ effect. There's also various other effects which I will briefly mention, but these are the kinds of things that we learn. One thing, and that many of these effects are summarized in the review article that we recently put out, so you're welcome to read, and there are many more actually like this listed for those of you who are interested in learning more details. One key takeaway is that we think that we can model many of these effects with aid of hydro simulation, but the one key challenge is that instead of looking at these properties as a function of halo mass, which is what a lot of cosmologists and astrophysicists tend to do, we really need to look at the diversity of the dark matter halos. At any given masses, the galaxy clusters, the dark matter halo could form in a very different way. Some form early, or some form late by having a lot of accretion at late time, so that this additional parameter called mass accretion history, assembly history of dark matter halo, is the key missing parameter. If I would argue today that if we can understand the halo formation as a function of mass and mass accretion rate, I would show you, I hope I can convince you or at least give you some promise that we can probably get some of these physics under control and develop accurate models for cosmology surveys in the future. Let me talk about this non-thermal pressure profile. This is a fraction of the non-thermal pressure provided by the turbulence and bulk motion as a function of radius, which increases steadily toward the outskirts because outskirts is where the accretion is happening. Inner region had enough time for the gas to dissipate energy and thermalize, and therefore there's not much evolution. This is a simulation from our Omega 500 shown in dotted line. These are the simulation measurements, and that it depends on mass accretion rate. In this case, we're using this parameter called gamma, the amount of mass accretion that took place between redshift of 0.5 and 0 as just a proxy. There are many ways of defining this, but if you split the non-thermal pressure fraction based on the fast accreting versus slowly accreting object just in the bimodal way, there's a clear systematic offset. And that the recently forming object, of course, has a significantly larger amount of non-thermal pressure, turbulence, and bulk flows. The nice thing about this is that we think we can understand this using very simple one-dimensional model of how the turbulent energy per unit mass, how that changes, and how that's controlled by the injection of turbulence and dissipation of turbulence. Just having this two-free term for injection efficiency and the dissipation timescale, but we also then relate the generation of turbulence to be sourced by the mass accretion. It's these accreting mass is the source of perturbation that creates turbulence, and so I'm going to make that as an ansatz. And that transfer of this dark matter accretion will also directly impact the gas, and in fact, if you make that ansatz, we can actually write down the model that captures both the radial profile behavior, dependence on mass accretion rate. We have a very accurate, we think we have a simple analytical model that can mimic this nonlinear effect of turbulence in galaxy cluster. That's what gives us a confidence that the issues of turbulence is less of an issue. We have a good simulation, we have an analytical understanding, we know what it is due to, we have a simple model. Another effect that you might hear about when you look at dark matter halo is that they're not spherical. We sometimes assume the halo as a sphere, and we make spherical assumption to just estimate masses within using hydrostatic equilibrium. We often make that kind of assumption, so that the dark matter halo ellipticity is another thing, which also depends on things like dark matter halo concentration, also the mass accretion rate. So there's a clear understanding of how dark matter ellipticity might be also correlated with the accretion history of the halo. We also looked at how the X-ray temperature, the scatter in X-ray temperature depends on the formation history or the ellipticity. They're all related, correlated phenomena. The early forming halos tends to be more spherical because they had more time to relax. Late forming halo, including those merging system, which of course creates significant asymmetry and departure from sphericity, they tend to lie below. The temperature of for example, the late forming halo is low because the late forming halo still have most of the kinetic energy in the non-thermal pressure form, which needs to dissipate in order for it to convert into heating. So temperature gradually goes up from late forming halo to early forming halo if you wait long enough. So we're kind of advocating the evolution from lower left-hand corner to right-hand corner for any given size halo, and you might be catching halos at different stages. So that's another physics and observable. Another thing I would mention is the splashback radius. Recently, people discovered that there's the outer boundary to galaxy cluster halo, the dark matter halo called the splashback radius. It's interesting because you can imagine a situation where particles are falling into the dark matter potential, but in cluster size halo is always growing. So mass is growing, potential is deepening. If the potential is static, then the particle that falls in from infinity, they will come in and then go out to infinity, obviously. But if you actually have a deepening potential, then the particle that is falling into the galaxy cluster size halo has more potential to climb back out. That will create the turnaround point out to which the finite point out to which the particle can go back out to, because you cannot climb out. You need more energy than what you had initially. So, but based on the energy conservation, that actually sets the limit of the outermost region called splashback radius, so that there's accumulation of the dark matter particle, and all the particle that fell in are accumulated within this thing called the splashback radius. When you look, so that's been known for quite a while, for the last 5 years or so. It became a little bit of a thing that you can detect using galaxy as a tracer. But then we can also ask the similar question. Well, how about the shock? Gas falls in, and the collisional gas falls into the center, and naively, the simple model will predict that the shock might be coincident with the splashback radius. In hydro simulation, we actually find the shock radius to be about a factor of 2 larger. There's a lot of interesting physics here for the reason I won't be able to explain, but the shock seems to be located about the factor of 2 larger region, and that there's an interesting phenomena that might take place. The gas is collisional, the dark matter is collisionless, and that the difference in collisionality leads to differences in these locations. I'm just going to mention one last thing about the cautionary remark about importance of plasma physics, and even in the outskirts of galaxy clusters. One thing that you actually can, that one can appreciate is that we have 2 kinds of fluids in gas. We have free electrons and we have ions. Most of the ions are in the form of hydrogen, a little bit in helium, very few in metals. But you can then calculate the equilibration time of electrons and protons. In the low density region in the outskirts of clusters, the density is of order 10 to the minus 6 per unit centimeters cube, and the temperature is of order 10 to the 6 Kelvin, like the typical IgM temperature. So there, if you calculate the equilibration time of electrons and protons, it's actually longer than the age of the universe. So then that's a bit of a problem, because then the electrons are thought to be out of equilibrium from ions. So the electrons are thought to be much cooler because through that cosmic, when the particle, gas particle go through the accretion shock, shock basically drive the particle, both electrons and protons, to the same speed. Okay? So what that means is that the ion, for example, hydrogen, which has 1,800 times more mass, 1,800 times more energy goes into ion, and then only that fraction, 1 part in 1,800, goes into electrons. All of this energy essentially goes to ion when the gas is shock heated at the cosmic accretion shock, 2 times the splashback radius. So that's interesting because all of the energy is in ion, and then it takes, like I'm arguing that it takes forever, like more than age of the universe, for electrons to equilibrate. Okay? So if you assume that if there is no additional interaction other than Coulomb collision, then that the electrons are going to be very cool. This is a simulation of 2 fluid simulation with electrons and ion, and I'm showing the electron temperature divided by gas temperature dominated by ion temperature. You can see that in the right around the accretion shock, that the ratio is almost 0, just stating what I just showed. And then after a little while, like after billions of years, you start to equilibrate. So these are the regions of highly non-equilibrium electrons. So if you're looking at the SZ effect and trying to map out the electron distribution, you're seeing very cold electron in the outer region. So if you assume that the electrons and ions are in the same temperature, then you significantly overestimate the SZ effect in the outskirts of the galaxy clusters. So this is just one effect. So here is just the effect of azimuthally average electron and gas temperature. It's of order 75%, the 25% effect in suppression of the temperature if you azimuthally average everything. Most of the mass is actually in the filaments. So this is why that you don't see 0. When you azimuthally average it, you kind of get the mass-weighted mean of about 25% effect. Nonetheless, in the era of precision cosmology, we can't allow this kind of uncertainty in plasma physics. This is the area where maybe plasma physics and cosmology and the collaboration might actually be needed in order for us to develop an accurate enough model of plasma physics. Just to remind you that those of us, anyone who's actually doing hydro simulation, the typical approximation is that we treat the fluid as a single fluid. We make that approximation all the time. If you're only talking about temperature and pressure without being clear about which species, then you are making that assumption. And then that also almost always assumes the local thermodynamic equilibrium, which means electrons and ions are in the same temperature. It's not the case in the outskirts of galaxy clusters. I will skip this part, but there's also significant advances in the modeling of aging feedback in the inner regions of the galaxy clusters. Now, I just wanted to show you some of the physical intuition that we have gained about the physics of galaxy clusters. But the goal is not just to do that. My goal is to actually then take those physical insights and then develop a physically motivated model for large multi-wavelength survey. We have to pay attention to computational efficiency because we're talking about very large data sets. So then our goal is to just kind of take all of this insight. Can we package this into a simple model that allows us to capture relevant physics, effect of cooling star formation, non-thermal pressure, shape of dark matter halos, clumping we didn't talk about, but our goal is to develop a simple, starting with a spherical Pell approximation, what additional modification do we need to make in order to make the model sufficiently accurate for future surveys? So that's the project called Barium Pasting Project that we're doing this in an international team of scientists, which I'm the PI of. So we have developed a model of gas density, pressure, density, temperature profile that takes into account dependence on the feedback, energy feedback that I briefly mentioned, amount of star formation rate, which is modeled by hand, effect of clumping, the fact that there's a substructure which creates boost only in X-ray but not so much in SZ, and that non-thermal pressure is also included in here. So we develop a model that are simply parameterized for astrophysics component, especially for gaseous medium, and then once you have the dark matter halo and the model for the gas, we can compute things like the autocorrelation and cross-correlation of SZ effect. This is Compton Y, X-ray, X-ray and Compton Y. This is a cross spectra. And also the X-ray and lensing, kappa, which is a convergence. So now we can start to develop this halo-based model that cross-correlates the dark matter halo with the gaseous medium. And then you can change the knob of some of the key physical parameters. And then since we have some ideas of the ranges of these parameters that we can also explore, how we can use these cross-correlation, autocorrelation signals to actually constrain these parameters or to actually quantify the systematic uncertainty in those future measurements. This is just the quick forecast of the kinds of constraints that we can get by combining CMB-S4 and Rubin and eROSITA. Without eROSITA in X-ray, we get this kind of constraint on non-thermal pressure model that we were talking about. Pretty good, but with eROSITA, very good. And that these parameter uncertainties are degenerate with some of the cosmological parameter like W naught, or that the energy feedback processes, so that we can now, once we have a simple model, we can also do statistical forecasts to see how well we can constrain various key physical properties of the galaxies and clusters of galaxies. Once we have that kind of model, we can also create a simple painting method. If you have n-body simulation, we also have a way of painting the spherical halo. It's on the left-hand side, and the aspherical halo. You can paint this onto the dark matter halo properties. If you use particle information, we can also do particle-based pasting, which particle information naturally contains the information about anisotropic distribution of dark matter halo, cosmic web, for example, which is important especially for KSZ. So we're developing halo-based model, but sometimes we really care about the particle-based pasting model, which is much more computation expensive, but we have two approaches, really depending on what we like to do. If you're just interested in counting number of clusters, halo-based for the thermal SZ effect, halo-based pasting is sufficient. It's 1.5 minutes for the map like of order 5 by 5 square degree of order 500,000 halos. Particle-based pasting is order of magnitude more expensive. So we are developing this kind of technology to quickly emulate the CMB sky. And that we can also do that on this is a comparison of the convergence map and Compton Y map, and that one can do this experiments on low resolution n-body simulation, which is fast enough to do, which has the 40 million halos, all sky survey, 100A realization, for which we have a convergence map, but we can also create thermal SZ and kinetic SZ map using this kind of technique. It takes about, it's pretty fast. It takes years to actually create this kind of map with the relevant resolution. Using full hydro simulation, we can do this in a few minutes, and then marginalize over cosmological and astrophysical parameters if it's needed. Okay, I'm going to skip just a couple of slides. Once we have that kind of parameter, we can also use existing X-ray observations to constrain the parameter or the degeneracy of these parameters. Here's this, in this paper, we attempted to use the existing X-ray observations from Chandra and Chandra observation. There's a Chandra follow-up of SPT selected clusters. So there are about 80 some objects in this sample with exquisite Chandra resolution, arc-second resolution. So you have a really good density profile with the tiny error bars for the population of galaxy cluster from redshift of 0 to redshift of 1.36, so that you can see the error bar is so tiny. These are observational measurement error bar from the Chandra data. Our previous model, like sometimes immediately failed to reproduce some of the features in the core. So we developed a model for Q-core that allows us to account for the departures, and that's actually teaching us a lot about the equation of state of the cluster core, which is basically governed by heating and cooling balance. So we actually have an empirical constraint using our model as a framework on the cluster core, but the outskirts are pretty robust. We can also use, these are mostly for the massive object, about 2 times 10 to the 14 solar mass. Yeah, one can also measure gas mass down to about 10 to the 13 solar mass in group range, which is relevant for eROSITA survey. And we can also put constraints on the amount of gas embedded within dark matter halo. And you can also see that the measurements are pretty exquisite. It gives us very tight constraints on the electron densities in clusters to group size halo. So with that, you get this all kinds. With that such small error bar, you get you can constrain all kinds of properties of the Q core, stellar fraction, gas fraction, non-thermal pressure fraction. Don't read this here. This is just to give you an impression of the kind of Markov chain exercise that one can do if you have a simplified model that are physically motivated, and if you have exquisite measurement from high-resolution targeted observation. This is the kind of game that we can play. Maybe I'll just show you leave you with the one upshot. For example, for one of the cosmology science called KSZ cosmology, kinetic SZ effect, which is induced by the peculiar velocity of the dark matter halo. One of the things you're measuring is the peculiar velocity of the halo multiplied by the optical depth, which is the electron column density. Electron column density, of course, is sensitive to the feedback physics, so that we need optical depth as a function of radius for the halo. In the context of our model, these current observation gives us exquisite constraint on the optical depths of order 12% in small size halo. In massive halo, it's a 4% accuracy. It's just that these very detailed model is giving us a precise estimate of things like the optical depth, which should not be a concern. So by developing this kind of computational model and then combining it with real observation, we can really marginalize over and constrain some of the poorly understood astrophysical parameters that are needed for doing cosmological analysis. Another thing that we can do if you have a halo model that has the properties of gas is to, for example, interpret X-ray power spectrum from EFEDS, which is the early eROSITA measurements. They made it publicly available. We have a model to create what kind of power that you should expect as a function of angular scale, so that we have the model that goes through here, and these are the measurement that comes out from the eROSITA power spectrum analysis. Below L of 3000, similar to actually also, you can do this also the SZ effect as well, which has been done using Planck. The halo model seems to do a pretty good job below L of 1000. But above that, it's actually dominated by the AGN background. In these regions, it's very challenging. We don't fully understand have good AGN models if we were to do this. But we can use the L less than 1000 to actually to study the the gaseous medium in groups, and also potentially doing cosmology. We're still not quite there. We have a work to do in terms of modeling AGN point sources and their population if we were to use smaller scale thing. So this is just an example of kinds of science that we can do. Let me just skip a few things. I just wanted to say a few words about the roles of machine learning in this. So we have a fairly large simulation data set that are becoming available. So one of the holy grail for doing, for example, cluster cosmology is to, after detecting, say, 100,000 objects, another key step is to estimate mass of each of these objects based on observable, either X-ray emission or the integrated Compton Y that you get from SZ survey. From that observable, we need, for every single source, we need to find some way of estimating mass of the dark matter halo that are producing that signal. So this is one area where the machine learning is potentially powerful. So this is the work that was led by the number of series of work that we have done, but also led by the Michel Namaka. Here in this example, we took the X-ray mock images of the 329 massive galaxy cluster from illustrious TNG 300 simulations, created X-ray mocks, and then we use some of them to actually train the model using convolutional neural net. What you do is that you feed X-ray images. You also know exactly what the true mass is in simulation. So you train the model to learn how to predict mass, just a single parameter, given the images. You do that multiple times. Some of the clusters are merging. Some of the clusters have AGN feedback going on, what have you. It will try to actually do its best to actually estimate the mass of a clusters. And in fact, when you let machine learning do this kind of exercise, and it's probably not a surprise if you have played around with this kind of technology, it gets very good estimates of order 8 to 12% accuracy, which is competitive, if not better, than some of the robust the mass proxies that I actually did as my part of a PhD. It immediately defeated my PhD thesis record. just based more on based physics and simulation based and try to make best guesses. My student who ran this code for me, she did it much better than I was able to do during my PhD. So that was disturbing in some sense, because just immediately your record being shattered just like that because this new technology that comes online. So of course I was skeptical, like why should I believe in this? I was in denial. But then I think that she convinced me that that it's actually it's understandable. One can actually interpret these results instead of kind of taking this as a black box. One can actually create a saliency map, asking a question: which pixels are important for determining, getting this kind of improving this cluster mass estimates? And she learned that they're asking these following questions: go to each pixel and then change its pixel value, and then ask a question: what kind of change in input cluster image is required in order to change the mass by some certain amount? So by asking this question and changing each pixel value, you can figure out which pixels are actually having the biggest contribution. And this is a distribution of pixel changes that seems to actually inform the cluster mass estimate. Most of them are lying in the outer region. Somehow they're not using the inner 20% of virial radius or R500. Well, that's consistent because my technique, I also knew that. Inner 20%, it has no information about cosmology or masses because there's stochastic aging feedback effect, which just generates a lot of stochastic noise. CNN is automatically learned to ignore the core, as I also learned to ignore the core after staring at the simulation for quite a while. Sometimes you get this kind of cluster. I'm including it just because you just can't ignore the. But sometimes there's like a bimodal clusters. So if you have two peaks, sometimes it's get confused as to where the central peak is. So you find somewhere in the middle, and then you get this just a weird outlier that looks something like this as well. But so this was kind of interesting because the machine kind of in the retrospectively picked up on the features that I was able to identify in simulations, and it seems to actually also contain even more information because I'm just pulling this as a function of radius, but we know exactly which pixels and which tidal features are actually playing a role in informing the cluster masses too. So that gave us more confidence in being able to interpret this machine learning approach, and then actually also teach us about feature I completely ignore. I was not able to use because I wasn't able to interpret such a large data set and pick out all of the features. The machine seems to be doing that pretty well. I can reverse engineer this, and then using this thing called the degenerative learning. After learning enough of this, you can also then learn how to emulate the galaxy cluster images. And this might actually be useful if you need to emulate many hundreds and thousands of objects. But in this way, we're going to condition this because we know from our physics experiment, we've learned that mass and mass accretion rate are important. So I think I can imagine doing this this process on not just on mass, but also mass accretion rate, which I hypothesize to be the most important secondary parameter of the dark matter halo formation. Then we can do this conditioning, and then so for any given mass and mass accretion rate, I should be able to emulate the SZ skies or X-ray skies with exactly the right amount of scatter, and also perhaps even predict morphology. That would be great. So this is what the exercise that one of our undergraduate student, Thibaut Rothschild, when he was still a freshman, just came out of high school, he actually did an internship in machine learning tech, and then he came to us, and then he decided to take on this question. I usually ask which one is the simulated image and which one is emulated version. I ask you to maybe contemplate in your mind and pick the one that looks to be the simulated or emulated. So one on the left, you probably guessed it because it looks a little smoother. I mean, this has more features. It looks like kind of overly smooth, but it kind of get the some of the double peak morphology. Yeah, I see that little artificiality and roundedness and smoothness, which is the artifact of this current CNN technique. So, but if I were to take these emulated images and make a plot of the scaling relation of integrated Compton Y as a function of mass, it reproduces the scatter almost exactly. Not too bad. And then if you actually look at the morphology, the YSZ concentration, how the pressure profile is peaked or not, extended. We have some concentration parameter based on how much signals in the inner 30% or outer 30%. It also seems to get that profile concentration reasonably well. We also have a symmetry parameter, which characterizes how departure from sphericity, and it also captures that feature reasonably well. As you probably noted, those of you who guessed it correctly, yes, it doesn't quite get the smoothness correctly, so that the generated cluster seems to be somewhat overly smooth. So there are successes. This is useful for various purposes of emulating many different versions, but now specifically conditioning things. We're learning how to condition things on not just on mass, but also mass accretion rate, giving us some insight as to, giving us a confidence mass accretion rate is probably one of the thing that's giving us rise to the scatter in SZ mass relations. That diversity is really important for us to understand. I just end by saying a few words about where we are going from the galaxy cluster science. I think the future is to actually go low noise, high resolution. And this is just an image to showcase what we have learned over the past decade or so from Planck, Chandra, Suzaku, which really just opened up a new views into the outskirts of galaxy cluster, which is mostly what I talked about today, and how to ignore the core, for the purpose of doing accurate physical modeling. And we've learned a lot of interesting physics and also ways to develop models around it. But I think it's really exciting opportunities that actually is also in galaxies. We do see these hot gas or hot warm gas embedded in galaxies as well. That field we have not had very much signal other than maybe from the HST COS, which has been developed here. And there's a lot of people who have worked on this. But that was about the sort of pencil beam approach to kind of get some ideas of the pressure, but was not as detailed like pressure modeling per se. But that field is just rapidly changing because of the HST COS revolution. This field is going to have H1 measurements. This field is going to have that measurements from X-ray and SZ that I talked about. Because the next generation of surveys are order of magnitude more sensitive, that it's going to detect the circumgalactic medium using SZ and X-ray survey, which is very exciting. In X-ray, you have to stack galaxies. In the eROSITA pixels, data already exist. One of our earlier, my former students have actually recently done that on the EFEDS data and was able to detect X-ray profile in different stellar mass and also as a function of star formation rate. But you can also then do that using SZ telescopes as well. So this is one of the area where the diffuse CGM, you might be able to map them out and do exactly the same kind of studies that I just talked about in galaxy cluster where emissions was booming. But now in this more diffuse area, which is slightly harder to detect, but probably in next few years, that field, and in fact, even as we speak now, the status of this field is changing. So that makes me hopeful and very excited about this new frontier on circumgalactic medium. The physics is very similar. If not, it's this massive smaller scale, so the effective feedback is more disruptive. The energy feedback from supernova and AGN will just blow out the gas throughout the entire virialized regions. But the hope is that there is observation from X-ray, and that this is a fast radio burst, can be used absorption line from HST COS, but more of that is coming or already in archive. And then the thermal and kinetic SZ effect, which this indicates the mass range and the redshift range, that they are kind of schematic diagram of what they are. They will likely probe in terms of mass and redshift space. Another exciting development on the computational side is that there's a new type of hydrodynamic simulation that Ben and myself are involved in, called cosmology and astrophysics with machine learning simulation, and it's called CAMEL simulations. This is a simulation, state-of-the-art simulation. So far is based on illustrious TNG models and SIMBA model. Now increasingly adding additional subgrid model, including Astrid model and a few others, and Ben can fill me in, or Bohr. But now, because that these are computationally feasible, that you can do, instead of just one cosmology, one astrophysics, and maybe vary aging feedback models once or twice, instead of doing that, the collaboration is now running 2,000 simulations of the same box. 25 H inverse megaparsec, small box for a start, for feasibility, but now people are doing 2,000 simulation, 4 in feedback physics parameters, supernova and AGN, 2 each, and then the omega matter sigma 8. So now one can start to create library of cosmological simulation in 6-dimensional parameter space, and the idea is to actually now these simulation will serve as a data set for machine learning to figure out the interesting correlation, undiscovered correlation between cosmology and astrophysics. And astrophysics is, I say this in a very broad term. It could be relation between stellar mass, merger rate, supermassive black hole, black hole mass, accretion rate. All of these are the values that we can measure for millions of objects that are in millions, the 2,000 of these realizations. We have this as a function of stellar astrophysical and cosmological parameters. So this will create ideal set for machine learning to figure out interesting correlations. Very important that you don't use just one model, because any given model could be phenomenological model. So the goal is to increase all of the state-of-the-art model, join this program, and hopefully we can learn astrophysics of the feedback along the way. So that's that led us to actually, Ben and I wrote together to this NSF program, which was funded as of just last year. We're still in year 1, and that our goal is to generate X-ray FRB 21 centimeter Mach in order to study how the CGM and galaxy behave and change as a function of cosmological parameter like sigma 8, which we already have in this simulation, or characterize how the supernova feedback or aging feedback, how that's actually changing the CGM properties. We have all the data sets in hand. Our goal is to actually develop the machine learning models, and then our ability to include any kind of observations. We're just limited by imagination. We have data set. We can create different kinds of data set. So I hope that I gave you just a glimpse of some of the exciting frontier in cosmology today. I think the computational frontier, machine learning has been very mature, which allows us to develop things like camel simulations, and that's the sort of next step big forward that we are involved in. I think role of machine learning is increasingly become more critical because of the enormity of that data set, not just in simulation, but also in observations. And then that there's new frontier in low energy, high resolution, low noise frontier that are being basically pushed forward by the instrumentalists who's just pushing that frontier in various directions, including CMB and X-ray, and of course in galaxy survey. So I'll stop here and I'll take any question. Thank you for your attention.
Hey, thank you, Daisuke, and there's a lot in there. And let's have some questions, and students first. I know I have some, so I'll look around. Feel free to think about it. I can fill one up right now. Did I see a hand? Did you go? Yeah? Oh. Did you push your hand up? Yeah, I did. Okay, here. And actually, no, yeah.
All right, thank you. You mentioned hydrodynamical simulations a lot. Not super familiar with them, but is there kind of like an issue then in approximating like kind of electrons and ions as the same species in a fluid, or do you think it's overseeable?
Yes, that's one of the topics that almost all simulations that I know of to date, except for the one that I showed, assume the local thermal equilibrium. So this is one of the few simulations where we explicitly went into simulation code and change and we included we treated electrons and an ion or gas particle separately. It's an extremely easy thing to do. It's a one-line change in the code, actually. Okay? And I hope you can appreciate that because, for example, imagine you have the gas temperature, okay? And then the only way that you need to track is how TE is changing as a function of time, and that